The following program is brought to you by Caltech.
I'd like to introduce our next speaker, Jim Bell, who's an astronomer and planetary scientist, a professor in the School of Earth and Space Exploration at Arizona State University in Tempe, and an adjunct professor in the Department of Astronomy at Cornell University in Ithaca. Jim's research primarily focuses on the geology, geochemistry, and mineralogy of planets, moons, asteroids, and comets using data obtained from telescopes and spacecraft missions. He's the payload element lead for the PanCam color stereo cameras on the NASA Mars rovers Spirit and Opportunity, and has been a member of the science teams on the NASA Near-Earth Asteroid Rendezvous, Mars Pathfinder, Comet Nucleus Tour, Mars Exploration Rover, Mars Odyssey Orbiter, Mars Reconnaissance Orbiter, Lunar Reconnaissance Orbiter, and Mars Science Laboratory Rover missions. Welcome, Jim.
Thank you. Great to be here. Oh, thank you. Thanks for the invitation to contribute to what's, I think, going to be a very interesting workshop. I think my presentation will be very complementary to Torrance's, although I have no theology to profess. And I was actually quite surprised that Hal got into the whole when is a planet born, the moment of conception debate, but that's okay, you know, it's all right. You want to have that argument, that's fine. We can debate that over beers later. I don't have a wonderful catcher's mask. I'm an observationalist, so for your theorists, just imagine that I have a 1 meter spherical force field around myself. So I'm going to talk about geology and geophysical observations of small bodies. And I'm going to come at this from a process perspective. So I'll talk about some of the diagnostic potential of geologic processes, observations of geologic processes on small bodies for understanding origin and evolution of these objects. And this is going to be a major focus of the workshop, of course. So I'll be talking about impacts, erosion, tectonism, and volcanism. I will intersperse that theme with examples from observations of primitive bodies. And as Torrance has pointed out, there's a large data set now of observations of comets, asteroids, and planetary satellites. Some likely truly primitive, others perhaps not. And so I'm only going to touch on some of them. I can't comprehensively do all of them. And then I'll just talk about some thoughts about future observations and getting at this theme that I think is going to pervade by design the workshop, and that is testability. I was teasing Hal earlier that he has the luxury of not having to be bounded by observations and testable hypotheses, and that's wonderful. But as an observer, we try to link what we see on the surface to specific processes and testable hypotheses. And this slide that Emily Lakdawala from Planetary Society put together is just a very nice synopsis of observations just prior to Dawn's mission at Vesta of all of the small primitive or sort of primitive bodies that have been visited by space missions to their correct scale. So Lutetia held the record for a short time as the largest asteroid having been visited by a spacecraft. And I'll touch on many of the processes and features going on some of these objects. We put that in scale. Here's Lutetia compared to Vesta, which is the subject of Dawn's investigation now, of course. And we can put Vesta in its perspective relative to Ceres and Earth and Moon. So we're talking about small bodies. We're talking about a very limited set of geologic processes compared to terrestrial planets, for example, but still a remarkable diversity and complexity of processes. And we start to think, at least I start to think a lot about where does geology begin to be expressed in small bodies. Of course, at large enough sizes, you can start to preserve impact craters without being completely destroyed. But there's a threshold size where self-gravity will lead to a spherical object shape, depending upon density of bulk density, et cetera. That's maybe 300 to 600 kilometers in size, perhaps smaller for more dense objects. And then you can start thinking about differentiation and gradational processes with significant gravitational forces involved. Larger sizes, more internal heating, volcanism, partial melting, tectonics. And somewhere in there is where people define this nebulous term of planet. I'm one of those weirdos that thinks there's 50-something known planets in the solar system, because I tend to judge an object by itself, not its environment. Has it had internal heat and complex and diverse and interesting geologic processes? But that doesn't make me popular, because then we have to make the school children memorize all these names, which would be horrible. So from the standpoint of planetary surface processes, there are 4 major geologic processes that we study on terrestrial planetary surfaces and small bodies: impacts, volcanism, tectonism, and erosion. And it's the combination of these processes, of course, that give us the observable features on these surfaces. So let me march through some of those. Of course, impacts are common geologic landforms on all spatial scales, from the comparable to the radius of the body, as on Matilda, which I'll talk more about in a minute, to large basins on the moon, down to tiny little things that we see in Mars rover images and other very small scale features on planetary surfaces. If you read or teach from Jay Malash's books, you learn about the key morphologic parameters that impacts that can be used with impact craters to deduce or derive physical properties or other information about the surface and subsurface, things like the diameter, the depth of a crater, depth to diameter ratio, the ways that the walls or other non-equilibrium features fail, the range of ejecta, whether there's impact melt in that system. And you can go through some pretty interesting details about, for example, depth to diameter ratio, and look at cases like the moon, where you get simple 1:5 depth diameter ratio up to a certain transitional point where you go from a simple crater to a complex crater. And this is driven by gravity. That simple to complex transition is a function of gravity, lowest size on the moon, larger for larger size objects. And so if we extrapolate out to the small primitive bodies, in theory, basically all craters for small bodies smaller than a few hundred kilometers are really sort of simple. They should be simple bowl-shaped craters. And so that gives kind of a basis, sort of a fundamental algorithmic basis for thinking about, well, how has that simple shape then been modified by subsequent geologic processes? Has it been infilled? Has there been some significant modification, erosion of the walls? Has it been modified by tectonic forces, et cetera, et cetera? So, so there's sort of at least in my mind, a simplicity to the use of impact cratering for small bodies, although as we'll see in some pictures in a minute, that there are some complexities that we run into as well. And of course, one of the things that geologists and photogeologists do is relative age dating of planetary surfaces by looking at number density of craters per square kilometer. So here's 2 images of the same body. It's the same number of square kilometers. Which one is older, left or right? Left, right? So that the standard answer is it's left, but there are assumptions that go into that answer. It has to do with the issue of crater retention, for example. It may be the case that this material just retains craters better than that material. I didn't say anything about the composition. I just said that they were on the same body. So there are a number of factors that have to be considered when we think about relative age dating. But in general, it's as a kind of a snapshot way, just through photography, to get an assessment of relative age dating. It's just a little animation that I stole from a Bill Hartman paper. As you build up craters over time, a bigger crater comes in, deposits an ejecta blanket, erases that, and its ejecta blanket either fades into the background or is destroyed. Maybe a lava flow or something comes out, and you end up with kind of a mess, and you hire an undergraduate to count craters. And, and this is really still relatively state-of-the-art kinds of basic relative age dating of planetary surfaces. And of course, there's an absolute age dating scale. I'm sorry, this came out kind of crappy, but there's an absolute age dating scale based on lunar samples from different Apollo missions that goes back to the oldest rocks in the Apollo collection to younger rocks that shows this strongly exponentially decreasing rate of impact flux with time. And most of the solar system is tied to that lunar impact flux model, and I've seen people with some trepidation extrapolate that out to Mars and asteroid belt, and I have, nobody knows really how well it works out there, although, people like Hal and Bill Bakke and others are thinking hard about that. But we really only have that sort of one pin point for this model of absolute age dates. So we use relative age dates and crater retention age, it's often called, to think about the stratigraphy and age relationships on small bodies. So Torrance mentioned Gaspra and Ida, the first two objects, first two small bodies encountered by spacecraft. So our first look at high resolution, tens to hundreds of meters per pixel on these surfaces. And work by a number of colleagues summarized in Rob Sullivan's Asteroids 3 chapter, for example, shows that there are multiple populations of craters on objects like Ida and Gaspra. So Ida has three populations that can easily be identified, sort of a fresh, young, small crater population sub-kilometer. And then curiously, two different populations of large impactors, smaller than about 6 kilometers and larger than about 10 kilometers. And the larger ones are predominantly on one part of the object, and the smaller big craters are on another part of the object. And this has implied to people, some people, the evidence for some kind of a change in the impactor flux environment that this object went through. So either the impacting population changed, but this is all very early, or the object moved to a different environment in the solar system. So, and similarly on Gaspra, two populations of craters, the young stuff and the old stuff, and the old stuff is degraded. And so Gaspra tells us that it may be the case that a single or small number of large impacts can completely influence a small body and affect your ability to basically reset the clock with ejecta deposited across the surface. So there are ways to use just simple crater counts and maps of them across these bodies to try to get at some of these issues that we'll be thinking about in the workshop of, what's the context for this crater and what kind of environment? Is it in a high flux environment, low flux modern environment? And I'm not saying that these are quantitative ways. I'm not saying that they may even be testable. But I think that's something worth poking into, because these are some sort of basic, simple measurements that we make at small bodies. It's hard to fathom a mission going without a camera, right? Although I guess people have thought about it. But there are ways, I think, to make these connections. Impacts also reveal stratigraphy. Just a couple of examples from some recent Vesta imaging, a beautiful example of a crater that impacted on the rim of a larger impact crater, okay, exposing, digging up a very bright higher albedo material. Another example from Vesta of a crater that has dug up darker, lower albedo material. And each of these cases are being investigated by the Dawn team with the detailed near-IR spectrometer data sets as well. So interesting ways to get at relative age dating and stratigraphy just by simply observing the impact crater population and its state of degradation on the surface. Volcanism is, of course, melting of materials and erupting onto the planetary surface, and on the terrestrial planets we talk about molten rock. But for some outer planets, satellites, and dwarf planets, we'd be talking about ice or cryovolcanism, where the water ice is the magma, or in the case of Io, of course, it's sulfur, and that's a prime example of outer solar system volcanism on what is hardly a primitive object, of course. But there's plenty of evidence going back to Voyager imaging and since in the Saturnian system and the other satellite systems as well for resurfacing events on these small bodies. So Mimas, Enceladus, Tethys, and Dione all exhibit areas like the example little test that I did before, where, and you can really see it very well in Tethys, there are large areas that have just a lower impact crater density. And so the suggestion is that there has been some resurfacing events, probably cryovolcanic, over time. Enceladus is, of course, the most spectacular active example of cryovolcanic or cryovolcanic-like processes in the outer solar system. Of course, a lot of debate about whether Enceladus is a differentiated object, is it really a primitive object, et cetera, but it gives us some really good ways to come up with observational scenarios. And Torrance and I were talking about, high phase angle imaging is the kind of thing you want to do, and we should be thinking about these kinds of tests for future missions to small bodies as well. Coming back to the asteroids, Vesta is actually about the same size as Enceladus, and there is this connection to the HED meteorites that suggest extrusion or some kind of magmatic processing of these to explain these achondrite samples. And in the Vesta data from Dawn, there's sort of weak but growing evidence for the existence of flows or flow-like features on the surface, and lots of debate among the Dawn team and the reviewers of their papers about whether these are impact melt derived flows or whether they are truly magmatic extrusions across the surface. And so that's some pretty exciting, but of course they're just sort of beginning that process as their mapping is about to be completed. From a tectonic standpoint, deformation of a surface from either internal forces, volcanic, tidal, or external. I guess impact and tidal is external as well. And faults, fractures, folds, all the common tectonic features that Southern Californians are familiar with are observed on a number of small planetary bodies. One of the most spectacular examples of a ridge in the solar system is this amazing 20-kilometer wide, and I hadn't been aware until looking up some numbers that it reaches heights of 20 kilometers relative to the surroundings as well on Iapetus. What the heck is going on here? These are, was it two bodies that are welded together? Was there some kind of crazy shock wave from a long gone impact basin? Pretty dramatic example of surface expression of what must have been some impressive internal forces. Similar kinds of features are even seen on Eros, which is only about the size of Manhattan Island. And it's, despite the gravitational, low gravity and relatively, well, despite the low gravity, there's a number of features expressed on the surface that indicate a pretty significant amount of stress in the interior, some ridges, grooves, and fractures on the surface. There have been models that invoke thrust faulting. And we're not talking about Mercury, right? It's not a planet that has shrunk from cooling. But it is an object that does occasionally pass close to the Earth, and Bill Bakke and others have talked about the tidal forces that are exerted on near-Earth objects when they do make very close passes with planetary bodies, and maybe just that kind of tidal extension on this very elongated object is responsible for the surface expression of these kinds of tectonic features. And so there may be ways through just simply observations of structural features and their relationships to learn something about what a very small body that does not have internal seismic activity from magma chambers and core mantle crust, what processes could that have gone through, and maybe that involves planetary encounters, and so maybe that involves it having gone through a very different environment than it is today. Again, probably not quantitative, but part of the toolkit that one would apply using geologic or geophysical observations. The classic example of grooves is the ones emanating from Stickney on Phobos. So some Viking and MRO imaging show these just in a spectacular form. Lots of different ideas about how they're related to the Stickney event, including some ideas that I believe claim they're not particularly related to the Stickney event. And so there's been a very complex history of deformation in this body. And up until Dawn got to Vesta, it was the prime example of grooves and ridges, and now the equatorial grooves and ridges at Vesta are even larger scale expression of probably related to this enormous impact at the South Pole. But one of the most impressive images I've seen lately is these beautiful radial fractures. I've seen them described as a sunflower pattern emanating from and around the South Polar Basin. So impacts are obviously a great potential source of the energy for that compression and tectonism, but I think tidal forces are as well. So this is, again, just sort of from the thinking from the Dawn team, and this is courtesy of Dave Williams and some of the things they've been talking about at their press conferences lately, looking at the surface expression of these ridges and grooves and relating them to specific areas on the planet, and specifically to these two proposed southern hemisphere basins, one older than the other. I forget their names. But there are at least two different systems that are expressed that are related to the pole positions of these two large basins. So small bodies do have tectonics. Kind of interesting. And small bodies have erosion as well, wearing down the high places, filling in the low places, driven by gravity and gravitational non-equilibrium surfaces. How do you move these things around? How do you do mass wasting on a small airless body? You need some kind of a perturbing force, and that can be tidal, that could be impact. We know these bodies are being hit currently by small impacts, and the features that can be created are the same kinds of gradational mass wasting features that you see on the terrestrial planets: landslides, talus slope streaks, and there are even some what are looking more like uniquely small body related erosional and sedimentary features, these so-called ponds like we see on Eros. I'll show a picture in a minute. Just some examples of mass movement and large-scale landslides, flows, perhaps impact melt, perhaps volcanic. On Vesta, here's a nice example of a big landslide. This wall of the crater failed and slid down into the bottom. So there are, again, gravity-driven processes to take disequilibrium surfaces and bring them down to equilibrium, and so that may have been, of course, triggered by an impact somewhere else. There's degradation, so just like we see on Mars, for example, with wind and weather degrading craters over time, or the Moon, where other impacts are degrading craters over time. Small bodies show craters in a variety of states of degradation, and some of them show, very nice examples of infill or mass wasting to change the simple bowl-shaped depth or diameter ratios that I was talking about before. So you can go back to the theory and make some inferences about how much activity, how much sediment, how much material has been moved around, and then perhaps back out some information about the kind of perturbational history these objects have been through. Again, maybe not quantitative, but another piece of the toolkit. I mentioned those enigmatic ponds on Eros. This is some work that Mark Robinson and Louise Proctor and others have done, and these were a really interesting feature to find because, first of all, you have to remember, before we got to Eros, there was a big argument about whether asteroids should have regolith at all, with gravitational attractions of forces of 1 centimeter per second squared and less. Why should these things hold on to any ejecta? Should all be gone? Are they just going to be bare bedrock with just super thin dust layers? But in fact, asteroids like Eros and many others are now known to have pretty complex regoliths, and very fine-grained particles move around in sedimentary cycles, perhaps related to perturbation from impacts or tectonic forces or electrostatic forces. These very small bodies with very fine-grained surfaces, some of which get fairly close into to the sun, so significant dust charging potential in those environments. And that stuff moves around, and follows, it can be ponded into equipotential surfaces over time. And so this was a surprise to see these kinds of, this kind of evidence, although it perhaps should have been predicted earlier. I wanted to just briefly point out another example of Phoebe, which may or may not be a captured KBO. It's in a retrograde orbit around Saturn, but I like this picture because it just shows this beautiful example of some slope streaks and mass wasting and some failure going on or preparing to go on here, and exposing what had been lower layers of stratigraphy that had been dug up and exposed in the crater rim. And so not only is it interesting just from a geologic process standpoint to think about, you know, what's happening to these forms relative to the theory, but it's also something that I'm not talking about at all, a way to potentially interrogate differences in composition and mineralogy. So, you know, you could take the, and I'm not sure if I'll bet you they're doing this, right? You take the Cassini spectrometer and point it in here and get at differences in potential composition. And I don't really know what to make of Helene. Some of you may have seen this relatively recent picture, and I mean, this is talk about resurfaced, right? I mean, there's a crater there, right? There's one there. I know this is like Io-like crater densities, but this is an icy body with a relatively modest density, thought to be modest density. It's not, density is not actually known. But just an enormous amount of sediment transport on this surface. I mean, these look like ski slopes in here, right? So lots of material moving around. What is driving that? Was there an impact recently that has, in fact, you know, covered the pre-existing surface with relatively fresh debris? Is it scooping up dust and other debris from the Saturnian environment, stuff that's being thrown off the rings, et cetera? This object is a Dione Trojan, right? So it's moving around with Dione, so it's dynamically kind of in a really interesting environment. And is it a coincidence that from a surface morphology perspective, it's showing a really unique set of landforms and features compared to other Saturnian satellites? Probably not a coincidence. So there's something, yeah, go ahead.
I was just going to say that the dynamics of these, the big difference between these things in the Saturnian system generally and asteroids and comets is they're existing in a much more dynamic environment.
Yeah.
You know, anything that gets off Helene's is going to go into horseshoe orbits, which have a high probability for re-impact. So the closest examples might be something like Phobos and Deimos, looking for that type of effect.
Yeah, and I didn't really talk about Phobos and Deimos. I think Julie's going to talk more about Phobos and Deimos, so I kind of left those alone. But
describe that as a depositional landscape?
my description is a hypothesis, and my assumption is that this is a heavily cratered body like other small satellites in the Saturnian system, and that something has come along and covered up what has been just sort of a background accumulation of craters. And so that's the assumption. I'm not sure how else to explain it not having a... So there's, what you can't really tell from here is the detail of the shape. So even though it's a very, you know, it's a small body, the gravitational forces here is like less than a centimeter per second squared, but there is downhill in this environment. And so if you get something started, there is a preferred direction of flow. And, you know, these look like, in a sense, sort of classic hydrologic drainage features. You know, material, fine-grained material following a downhill slope. But, you know, somebody tell me if I'm wrong. I don't know if anybody knows what's going on here, but that's sort of, from an analogy standpoint, that's maybe a simple explanation.
We don't obviously have a detailed gravity map of this,
right.
But from the shape and assuming uniform density, most of the stuff is ponding in low gravity.
Yeah.
I think that's another theme that runs through this. If you look at the comets, everybody says every comet looks different. Practically every comet we've had a good look at has got material ponded in low gravity areas.
Yes, I'll come back to that in a moment. Good point. So, you know, I mentioned these high-level geologic processes that we think about primarily for terrestrial planets, and how do we apply them and understand them for small bodies is is a challenge because we often don't have analogies among the terrestrial planets for such low gravity environments. But there are other sort of direct and indirect clues about process and properties that can come from geologic observations. You know, taking pictures, variety of angles from orbit, stereo imaging, etc., allows you to get topography and shape data, which can let you get a very good estimate of the volume of the body. You take the volume and mass data from flyby trajectory analysis or gravitational field modeling, and you get a density, right? That's the one number that a lot of theorists especially really want to know about an object. It tells you about the interior in a coarse bulk sense. You can do the same kind of thing if an asteroid or a comet has a satellite. You know, Kepler and Newton will tell you the mass of the primary within some constraints, and so you get your volume measurement. You can again get a good estimate of density. A lot of work recently on estimates of porosity from these mass and density measurements. Some new work that's being done using the VESTA data on looking at crustal density anomalies by taking the topography out of the gravitational field mapping and seeing what's left over. And then I'll mention cometary nuclei, and the best I could come up with is considerable confusion about the geology of comet nuclei. And I'll talk about those briefly. So most asteroids are rocky. This is density on the x-axis and mass here. But there's a number of them that have relatively high mass and low density. And there's some compositional information that tells us that these are not icy, at least on their uppermost surfaces. So you can sort of recast that, as Dan Britt and others have done, into estimates of porosity. And here's 0%, here's 80%. And so these authors sort of group the known asteroid, the spacecraft encountered asteroids into three different categories, sort of standard rocky bodies with standard rocky bodies with very low porosity, kind of middle of the road, moderately porous, and then very porous objects based on their high mass but low density. So, and you can, there's about the same number in each of these populations so far. So is high porosity typical? There are lots of ideas about what happens to an object like Matilda, which is one of those very highly porous objects as deduced from that previous plot. What happens to an object like this when you basically create a global-sized impact crater in it? There was enough energy likely to completely disrupt that object, but that energy was taken up in compression instead of fragmentation. So you end up punching these big holes in it, and some people think that you keep doing that over time. You build up you decrease the porosity through compression until the object is completely disrupted, and then you start the process over again. Maybe you completely fragment it, it comes back together, or you just completely destroy it and start it on the fragments, etc. But observations like this really, I think, provide a lot of good information about this idea of rubble pile versus coherent bedrock. And I don't know how you guys deal with this when you're accreting. You don't think about porosity probably, right? You just build things. And so is a porosity, high porosity, a natural outcome of the accretionary process or not? I guess if we start seeing more and more high mass, low density objects among the collection of spacecraft observed small bodies, we might lean more in that direction. And I'm not sure how that'll influence the theory and dynamics, but it's going to have some role in it. At the another example of small and very porous body as deduced by mass and density estimates is Itokawa, and Torrance touched on this as well. Very, very small object. One of my favorite pictures is a spacecraft looming above the surface there at 0 phase. And this is a little lump. It's about the same size as the object that OSIRIS-REx will visit and collect a sample from. This is an S-type asteroid. The OSIRIS-REx body is a C-type, so it'll be, in theory, different composition. But there aren't any craters, or maybe arguably there are some craters, but they're not very prominent on this small body. And so probably because it can't take them, even though it has low porosity, it's probably they're disrupted remains of larger bodies that have been fragmented over time. But it's very confusing to interpret this surface as well. There are these low regions that have this fine-grained material that ponds up in equipotential surfaces, which are not always flat on strangely shaped bodies. They can be bizarrely curved shaped surfaces, so you need the shape model to figure that out. And it's, I guess, arguable on whether there's any regolith in places like this where you're seeing individual rocks and boulders and some pretty precariously perched materials up there. And I mentioned gravity anomalies. Here's an example again from the Dawn team's press release stuff, showing the kinds of work that they're doing, taking the topography out of their gravity field data. Now they've got some wonderful stereo imaging, so they have a very good shape model of the object, and they can do the kind of free air gravity anomaly work that you do in classic geophysics, and see that there are crustal density anomalies associated with areas like the intersection of these two basins and the central peak of the large South Pole Basin. So there's ways to probe the interior through sort of geophysical-oriented global imaging, topography, stereo imaging, and if you're in orbit around an object, getting that gravity field data. Just a few slides about comets because they frighten and confuse me. We're increasing the sample that have been imaged by spacecraft. Are they all going to turn out to be different, every single one of them? I don't know. There's a trillion or so to choose from, so that would be kind of interesting. But the sample so far is really diverse in terms of surface process. Tempel 1 has these, this is the deep impact site. And while everybody was looking at that and getting excited, the geologists are looking up at this, right? These beautiful layers. There's a stratigraphy. It wraps around the object. Some of that terrain is being eroded. Are these layers? Is this an onion skin structure that was somehow built up in layers of different material? Or are we seeing some surface expression of preferential erosion because of these jets and small-scale regions of evaporation or sublimation? Lots and lots of puzzles. This is also, remember, a very low-density object, 0.4. So how do you reconcile that with the likely very porous and fluffy nature of the interior? There's all kinds of interesting active processes happening on this surface. These circular features, are they impact craters? This is an object that is shrinking with time, that every perihelion passage it's losing a significant amount of mass and surface. And so, it's not like there's this ancient structure of buried impact craters that are being exposed, or is it? What exactly is going on? It's a lot of puzzles in here, and then you look at something like Wilt 2. What are these circular features? Is every one of these a caldera, a cryovolcanic caldera, or are they impact craters? Some of them have raised rims. They're depressions. I have no idea, and so these are puzzles that are still being worked out from the available data, and it's likely that additional cometary encounters are going to show additional diversity as well. There are terrains on Tempel 1 that mimic this kind of structure, circular pitted and irregular structures. So maybe it's a common feature on cometary nuclei just because of the sublimation process. We just don't know enough, haven't seen enough examples of them to say for sure. So what's coming in the future? Torrance mentioned a few things. So Rosetta will get to Churyumov-Gerasimenko, I believe next year, 2013 or early 2014? Early 14, right? And we'll spend a number of years watching this cometary nucleus go from its relatively more quiescent outer heliocentric environment through a passage closer to the sun, and that is just going to be really interesting to look at changes in this environment. First time that we'll spend some quality time in a cometary environment. Of course, Dawn will go on to Ceres. Lots of interesting debates and predictions about whether that will really be NASA's first KBO mission, maybe. If you stir things up enough, than objects that formed much farther out. Some of them are going to end up closer in, and Ceres is a great candidate because of its density, because of its composition, more volatile, rich composition, to be an object that formed farther out. But who knows? I think most of the bets are that it will at least look very different than Vesta, and which will make for a pretty interesting mission. Of course, we'll get our first look at the sort of classical Kuiper Belt objects, Pluto and Charon, with New Horizons in just a few years. OSIRIS-REx will visit a small C-type asteroid and bring some samples back. And then there's a number of opportunities in discovery, new frontiers, and various programs that the Europeans are considering for small bodies. And Torrance mentioned those as well. And my expectation is that increasing the sampling of these objects is just going to increase the diversity of surface geologic processes that we see, probably increase the number of puzzles that we find as well. Because traditionally, planetary geologists are trained by looking at the moon and looking at Mars and looking at Venus and going into the field, and we're in these high gravity environments, and we don't have analogs for many of these processes or circumstances that exist on these particular bodies. Extreme ranges of temperature, vacuum, low gravity, difficult things to simulate, even if people send you money. And Torrance mentioned the survey, and this is the key questions table from the survey, and I've just highlighted some of the issues that in green here have to do with primitive bodies. Lots of them. The survey, I think, has done a great job of outlining some of the key priorities for science questions related to primitive bodies, both in terms of building them, putting them together, and incorporating them in the classical larger planetary bodies of the solar system. Thinking about the ways that some of them could be the sources of volatiles for inner planets like the Earth, like Mars, perhaps Venus, of course. And then thinking about potential hazards from near-Earth objects as well. There's a really nice story that is developed in the Primitive Bodies chapter and embraced by the community through the survey for continued study of these objects. So let me summarize then. Geologic and geophysical observations of primitive or semi-primitive bodies, depending on what your definition of primitive is, allows us to look at geologic processes on a whole different stage than we're used to for the terrestrial planets. But it's the same kind of processes, fundamentally the same kind of physics going on, just with some significant modifications in the variables, so impacts, tectonic features, erosional features, even volcanic features. And I think there are ways to start to tie those, maybe through models, maybe through speculation, to different scenarios for origin and evolution of some of these small body populations. There are some other geologic observations that we can make that are directly related to obtaining geologic and geophysical measurements like density, porosity, looking at spatial variations in the impact crater size frequency distribution and the degradational state of craters. And those, I think, can be used to provide some constraints, maybe soft, maybe hard. We can argue about that over the next few days on formation models and surface interior evolutionary pathways. And then finally, I just have to wonder what surprises await. There is a giant sample of unsampled populations out there in the Kuiper Belt, among the Centaurs, among the Trojan asteroids. Torrance, you didn't mention that Trojans are on the list of new frontiers for as well. And when I go into schools and kids ask about asteroids, and it used to be I would say, oh yeah, they're all between Mars and Jupiter, and there's 1 million of them bigger than a kilometer. And now I have to tell them, well, there's 1 million of them in these 2 Trojan clouds as well, and it's just a giant population of unsampled bodies, and the Kuiper Belt's another one. And it's likely that we'll be surprised and delighted by what we see on those surfaces, and hopefully educated as well. So I'll end with this really nice summary of sort of where we are, add Vesta to that mix on this scale, and I think it's a pretty exciting time for small body geology and geophysics. Thank you.